Hello mathematicians, we're now going to take a look at aspects of the further calculus topic, and we begin with differentiation of the 6 trigonometric functions. Now before you panic, there aren't 6 as far as I'm concerned. What we need to be able to do is to differentiate the 3 main trig identities which we've encountered so far. So the differential of sine, the differential of cos, and the differential of tan. Now we also can work the differentials of the reciprocal identities, and we use either the quotient rule or the chain rule to actually work these out. So although the textbook says that you should know these next differentials of the reciprocal quantities, I don't think that's the case. In fact, I'm sure that's not the case. So commit these to memory if you wish, if you've got enough spare capacity in your brain, but I would think if it turns up, it may even turn up as a question for you to prove that one of these reciprocals differentiate to be the format that's shown here. So I would ignore that. And when we go to look at the exercises in the textbook, I've really just selected from the first few exercises because I think that the text does the usual trick of making some extreme examples later on, often with a view to those students who perhaps are doing extension 2 at least. So I think I've selected questions 1 to 7 for you to do out of this exercise. I'm going to do number 8, and it's already getting on, I think, in parts, the extreme form. So the first little bit says, differentiate sec x tan x and show that it equals this. Well, that's okay. I think that's a reasonable question. But it's still not an easy one. So the first thing is to recognize that we're dealing with a product, this by this. So by our product rule, we put down the first, differentiate the second, plus put down the second, and differentiate the first. So we need to differentiate sec. Now, rather than have memorized that the differential of sec is sec x tan x, I think you should be able to do the differential of sec by recognizing that it's cos x to the minus 1. Just be careful about how you write that, so it's definitely not cos to the minus 1 of x, it's cos x all to the minus 1. It's 1 over cos x. So if we differentiate that with, well, you can please yourself, the quotient rule, but I would just use the function of a function rule, so that will become minus cos x to the minus 2, so that's why we've got cos x squared on the bottom, and it's now okay to write cos squared x. So minus cos squared x on the bottom, then we differentiate what's in brackets, so cos differentiates to minus sine, so together those two minuses become a plus, and we're left with sine on cos squared. One of those coses will give us sine on cos is tan, and the other cos, which is on the bottom, is sec. So we've got this step here, take out sec as a common factor, and we've got sec squared from the first term and tan squared from the second, and then because sec squared is 1 plus tan squared, or tan squared is sec squared minus 1, then we end up with the expression that we're after. So I think that's a reasonable enough question. Not easy, but reasonable. The next one I'm not too sure is reasonable. So find the values of x for which this function is decreasing in that interval. So we should definitely know what it means to be decreasing, and that is that the slope is negative. So d dx has to be negative, and we've got what d dx is, which is this thing here. So normally we would say, well, we'll look for critical values. So they're the ones when values of x which make this expression equal to 0, and then we'll investigate what's going on near them. But when we do that, we can see that sec x equals 0 is one possibility, and sec x equals plus or minus 1 on root 2 is another possibility, algebraically. But for both of these, they're undefined. If we go to solve those in the calculator, using sec x is 1 on cos, therefore we flip these upside down, then we're going to be dividing by 0 in this case, and we're going to have cos outside the range of cos values in this case. So where you go to from here means that you have to look back at the actual curve itself, the curve of sec x tan x. And to do that, I think is really extension 2 work, to look at the curve of sec x tan x. And the curve looks like this. We can come up with it by taking a few critical values. So for example, tan x is undefined at pi on 2. So the product will be undefined at pi on 2, or at multiples of pi on 2, which is here and here. So in the domain that we want, that means that the curve is undefined at pi on 2 and 3 pi on 2. And then really, to see what's happening in between, we just take test values. So what we can see is that the curve is decreasing in between those two asymptotes. So pi on 2 less than x less than 3 pi on 2. But I don't think that's a reasonable question for extension 1. So I wouldn't even attempt any of the later questions in the exercise. So 1 to 7 should be testing enough. So what's the big idea? Well, there isn't really no extra big idea here. It's just recognize that if we can differentiate sine, cos and tan, then with the rules we've already got, we can differentiate sec, cosec and cot, and be prepared to apply them. And then have a go at these questions in 6A.